And well, he said that he is confident with his explanation. But I'm not that for sure for that. And recently, in recent notice result this March, these people, they show that maybe this is due to the C quark effect. Some person there mentioned this result. Yeah, this is because of okay. This is because of this loop. So okay, this basically this is related to the so for gluons, because gluons does not carry electric charge. So basically, gluons naively gluons will not feel electric magnetic field, right? But the gluons can feel electric field due to the quark loop, because quarks can feel magnetic field. So basically, the gluons can feel magnetic field due to this quark loop. And also because how to say? Well, some kind of details here, because previously some lattice groups, they use quenched lattice calculation, and they didn't get this inverse magnetic catalysis, because for quenched lattice, basically there is no such kind of quark loop there. So basically there is kind of gluon system. So basically, so there is no. So basically, they still found such kind of magnetic catalysis. But this result, lattice result, is for physical quark mass. So basically, you really need a pion mass, very small pion mass. And so basically, in some sense, they said, okay, so this is might due to this kind of quark loop. So this the gluons, and also they actually showed this product loop as a function of EB that. Of course, you can extract this TC by yourself. So you see, so you can basically, you as I told you, you can just, the peak is around here for zero magnetic field. So basically, the TC is around 170 something. And for this, when magnetic field becomes stronger, so you can say this, you can actually extract by yourself this TC indeed also decreasing. So basically, you can also have inverse magnetic catalysis. Inverse, it's not magnetic catalysis. Inverse behavior for collapse flow, for deconfinement. Okay, I think Henry might, I don't know, but he said there is no result, but indeed this is the result for lattice. Okay. But tomorrow I will show you our recent work on this, how to explain this inverse magnetic catalysis by using a spinor effect. I will explain tomorrow. So I think in this lecture I covered basically the strongly coupled QTP here, and cover superconductor here, and also this QCD matter and magnetic field. So I think still many interesting things are going on. So I think for young people, you do not need to feel very disappointed, because maybe eventually everything goes. Basically you can go back to a very simple phase diagram, but still many interesting physics still there. So I think for young people, you still have a lot of things to do. I think it's enough, at least for your PhD thesis, right? Okay. So I think maybe I don't mention this electron ion collider because I'm not an expert there. I'm not an expert for this EIC, but this is getting very hard because in mainland we have this EIC project. This is actually approved. So we will have a here in Nanzhou. So this is for electron ion collider. And of course, there are many projects going on, might be going on. So this is from US. These are not approved, but still many things going on. I think this part is also very important for young people. I'm not expert, but I'm learning. So I just tell you this project is trying to understand the rule of Grom's and sequence of QCD. So in this part, they going to understand the nuclear spin structure, and also the Grom situation at the small x, and also they have QCD phase structure of cold nuclei. So this is basically understand the nuclear structure. I think this part is also very important. It's I think I stop here, and thank you very much for your attention.
Question?
Oh, sorry. 10 minutes.
Comments?
So how to understand the difference of what to say? It's a crossover and phase transition. How to understand that?
You mean how to understand the crossover, the difference between crossover and phase transition, or?
Oh yeah, yes. How it happens? How it snares the?
Okay. So this is a kind of okay. So basically, for crossover, how do you say it? Everything that so, for example, I mean here. I think for QCD phase diagram, I think for sure that so this part, low temperature and low density, this is heterogeneous, right? And for sure that at a very high very high energy, very high temperature and density, this is a quark and the gluons, degrees of freedom. I mean, some matter made of quarks and gluons. So what really different is that, okay, how this phase goes to this phase, right? So, okay, so if you have a phase transition, basically, so this phase goes to this phase at a certain temperature, right? So basically, this is not a region, but this is a line. But for crossover, that okay, so this basically tells you that okay, this transition happens very slowly. So it's kind of still there is a transition, but very slowly happen. This year, yeah, I think for these two phases, it's no problem here. So the problem is okay, how this happens. I think this is a difference. I mean, for real phase transition, this happens. This is just one phase transition line. But for crossover, you have a kind of regime that crossover regime that this from one phase crossover to another.
So is it related to the string breaking, or I mean, string breaking makes more makes the concept of the confinement more. It becomes more not solid. So
string breaking actually. String breaking, I would say, is not a good measure for confinement and also not a good measure for deconfinement. Because for confinement is this linear behavior, is this linear potential, not the string break. So this string break is kind of like you put, okay, let me, okay. So this is kind of, string break means that you have physical quark mass. So if this is permanent confinement, so basically this is like quenching QCD. So quenching QCD, I mean this is kind of permanent confinement. But the string break means, okay, you can, I mean the string can break because you, I mean this, because you can excite this quark and quark degrees of freedom.
So I just thought that the threshold of the string breaking just drops. It becomes just a different phase. It's my naive expectation is just a string breaking.
Yeah, okay.
Is a lower.
Okay. This actually, okay. I will come to this tomorrow. I mean, how this behaves. They have a lattice result. How for this potential. Have a potential how this melt when temperature increases. But I think the string breaking itself is not a good measurement for confinement. But maybe you have something else in your mind.
If there was no chiral, if we had a theory where there was no chiral symmetry breaking.
Sorry?
If we had a theory where there was no chiral symmetry breaking,
yeah,
but it was still a theory like QCD with fundamental quarks, right? Would we see a deconfinement transition? Probably no, as a function of temperature. Because
so you mean you have
I'm just ignoring chiral symmetry breaking for the moment. I'm just thinking about Yang-Mills with matter in the fundamental representation, massless quarks. Now, in such a theory, we cannot just make a distinction between confined and deconfined phases because there's no order parameter. So that would probably mean that as you increase the temperature, there's no sharp deconfinement transition in such a theory. So, but in real QCD, there's another thing going on, which is also the chiral symmetry breaking. So we don't know, but I mean, the transition that we may expect between low and high temperatures is probably tied also to the fact that there is a chiral condensate. I'm just trying to answer these questions.
This question, I see.
Yes, that the putative phase transition that you were looking for is probably because there was a chiral order parameter.
But we look for both. We look both. I mean.
But I mean, I would never expect for. I mean, what is the order parameter for deconfinement?
Yeah. Okay. As I said, this is a kind of order parameter at two different limits, right? Chiral condensate is the limit.
But there is no rigorous order parameter for confinement.
Yeah, this is exactly what I want to say here. So this is a kind of energy. I mean, sorry, where is my perspective? This is actually what I want to emphasize that chiral. I mean, the order parameter for chiral phase transition and the order parameter for deconfined phase transition. Basically, they are defined at a very different energy scale. I mean, one is for massless quark, and then one is for infinite quark mass limit. So basically, I mean, it's a kind of, I mean, naively, I would say, what's the relation between these two? So basically, you can, in principle, you can, basically, these two phase transitions can be separated, even in. But I still don't understand why in chiral limit these two happens together. So this is actually I don't understand. But this is not his result. Okay. Yeah, still I think still something I'm not really fluent.
question you can discuss later. So it's just thanks.